Today we are going to do section 2.5 on page 186, which is equations of lines and planes in space. Now the equation of a line is, well, first let's talk about two vectors that are parallel. If two vectors u and v are parallel, then they have the relationship of being one being the multiple of a scalar multiple of another, and the scalar multiple can be calculated by dividing their magnitude. Now with that information, what we're going to do is that to represent a line in space, well, we're gonna do two things. First, we identify any two separate points in the line. See, here's our line in space, and then we'll pick two different points, any 2 points from P to Q. P will consider it fixed, and Q will be just any other point on the line. Now, from P, if you do P, Q minus P, that is, you get the vector from P to Q, right? So PQ vector will be Q minus P, and that will be equal to some vector like at the origin, which we will call it some vector that's parallel to the line, but at the origin we'll call that equals to V. So PQ will be equal to TV for this principle if V and PQ are parallel. And if you can find such a V such that it's parallel, then we have from this particular equation we come up with a bunch of equations such that x minus x0, that's the PQ. Okay, so we'll write out PQ as in the 2 points subtracting x minus x0, etc., which TV is equal to T times ABC. And that is going to give us the equation of the line. Now, if you go on a little farther, then what you get is basically, then we have the equation, the vector equation of line right here is equal to R is any point in let's see, yeah, any point xyz on the line is equal to R0, which is some initial point we pick, doesn't matter where it is, plus T times V, whereas V is the parallel vector. So remember, the vector is something that has a magnitude and a direction, but it doesn't have any specific location. I mean, it's just located, that is, it's just located at 0. At the origin, that is, its base at the origin, and then it shoots up normally. So that's how you normally draw a vector. So the parallel vector is so vector has magnitude and direction only, and we don't care where it's located. It can be located wherever, right? So the two vectors then have that relationship, which is enough for us to calculate the equation of a line in vector form, which is right here, R equals to R0 plus TV. Oops, sorry. This thing shrunk down to nothing. Okay, let's try again. So this is our vector equation of a line. Now that can be rewritten, being that this is a vector equation, it has 3 parts. Now look down here, the 3 parts are called the parametric equation of a line, where x equals to x0 plus ta, and similarly for y and z. And that's how you represent a line parametrically. You can even, being that these t can be isolated from the 3 equations, you can also write it this way. It's the same thing, different name, and this is called the these things where 3 things equal to t, you just write them to be all equal, like and they are called symmetric equations. Look down here a little bit. Then you see the symmetric equations down here, okay, which means these things equal to t, and each one of these equal to t, and that is equivalent to the parametric equation up here, which is equivalent to our original vector equation up there. So all these equations says one thing, is gives the parametric representation of some line. Now, so with that, please do example 2.45, where you are to determine the equation of some line in space. In this entire section, you're pretty much finding some simple formula Well, simple as in not, it doesn't involve calculus or anything, but extremely tedious because you have 3 things to do, right? Not just one, because you're in 3D, now you have to calculate stuff in 3 dimensions. So it's gonna take a while. Now, sometimes we don't need the entire equation. We just want to control a line segment specifically from P, some space point in P and to Q, and we want to control T that way. Now, if that is the case, a bunch of simple addition stuff you can calculate. Say P is the boldface P is the original coordinate, x0, y0, z0. And then you have T times P to Q, whereas Q is x1. And by the time you manipulate these things slightly with some addition, you end up that your equation is going to be 1 minus T times P plus T times Q, whereas P is the coordinate, is the variable for the coordinate of the big P, the point P, and then Q is the point of point Q. So the R, as you vary T from 0 to 1, then you can get just the line segment exactly from P to Q. So having said that, and that of course can also be written in parametric form too, in which you can see better what's happening. In parametric form of this vector equation, it just means that you write down all three equations, and which becomes down here. See, x is that relationship, and y is in a symmetrical relationship, so is z. Okay, then each of these variables will eventually come up with will help you come up with a straight line in space. So when we say line in math, we always mean the straight line. If it isn't straight, we'll mention it. I mean, we'll specify it. So a line is always a straight line, and so is a line segment, is straight. So so please do example 2.46 as part of your homework, where you are gonna have to, deal with some addition. And by the way, I should mention that Desmos has a 3D version, the graphics calculator, so that you can plot parametric equations in Desmos if you want. I will mention that in the next section. Right now it's just lines, is not that big a deal, or planes. So yeah, but it can be plotted in the 3D graph, and also you can move the 3D graph so you can see it in different angles to get a better feel for the 3D that you're plotting. Next, let's go to page 190 when we consider the distance between a point and a line. Now, the distance between a point of a line, even if the line is 3D, the scenario is always in 2D. That is, you can put the point and the line all on the same plane. The plane isn't necessarily a standard plane, but it is a plane. You know, some plane in space that you can contain both items. Oops. And so then if you have that, then what happens is that then you just consider, how would you calculate the distance? Well, the distance is the perpendicular line, but how would you calculate that? What happens is that first you will calculate the vectors, okay? Because the vectors, what you're gonna do is pick some point on the line, we'll call it point P, all right? And then with point P, and then we'll pick another point on the line, and let's call it, doesn't matter where it is, okay? Just finds another, that is, we find a vector that's V, that's perpendicular to the line by finding another point on the line so that we can calculate this vector. Doesn't matter how long it is. And then we're going to similarly make a vector from P to our point M. And then we're going to take, what is this? Some product, cross product, no? Okay, then, that is what we're going to do. What we're going to do is now we have the parallelogram to think of, okay? Because with two sides, we can draw a parallelogram, and that gives us, then in which case the cross product between the vector V and the vector PM is going to be the area of the parallelogram. Then you remember to calculate the D, which happens to be the height of this parallelogram. Then you remember that the area is the total area divided by the length of the base, which is going to be the height. the distance. So that gives us this easy formula. See, to calculate the distance between some line and some point and some line, you calculate from any point on the line to the point times the vector of the line, doesn't matter which one, and divided by the vector. When I say times, I mean cross the vector, and that will give you the distance from the point to the line, which is a pretty nice, comfortable formula because everything is in 3D, and even though the principle is simple, actually doing it, if you just blindly do it with the old stuff we already know in geometry and stuff, that's going to be a total pain. Whereas this gives us a somewhat neat, direct way of getting it. Of course, you still have to calculate what the vectors are, what the magnitude of V is, and also what the cross product is, which is still tedious, okay? So please do this tedious work. It will be very good for you, and it builds character and everything. And please do this example 2.47 as part of your homework. I think I forgot to mention example 2.46, where you calculate the equation of some line segments. So please do that as well as your homework. And then with that, we will look at Now in space, we have several possibilities when it comes to lines in space. First, two lines are exactly the same line. That is, they're identical every part of the way, and they're called, in that situation, they're called equal. Next, two lines are parallel but not equal. That is, they go in the same direction, but they're just parallel lines. They're not actually equal, like, well, I suppose, like any parallel line, except that it's in space. See, it just pretend my arms are lines, then you just you have, well, yeah, parallel. See, and but they can go whichever direction. Now those are the simple ones, and the third ones, if the two lines might intersect in space. Okay, if they intersect, remember, a line, unlike my arm, a line does not have thickness. Imagine my arm to have no thickness at all, or width, or anything. They're just two lines. So then that's how they would intersect. They only intersect at one point if two lines intersect in space. And if two lines intersect in space, they define a plane. That is, those two lines together, there's exactly one plane that contains both lines that's intersecting. And lastly, excuse me, the interesting part is two lines that are in space, not parallel, but does not intersect. The reason for that is because you have a third dimension, right? If you lift the line up, they sort of cross each other. They get to the closest point, but then they take off because you got a third dimension. You can't do that in 2D, but you can totally do it in 3D. So that's called the skew lines. And then as a result, I want to remind you to do the student project, which is to calculate the distance between skew lines. And I think that's fairly interesting. The student project on page 204. Please do that as part of your homework as well. But not right now. Right now, we're still looking at example 2.48, where you are given various lines and try to figure out what they are: equal, parallels, intersecting, or skew. So please do example 2.48 as part of your homework. It is, again, some kind of a basic algebra that you're going to be doing. Next, let's go to page 194, where we're thinking about a plane now. How do you define a plane? The plane in Euclidean geometry says a plane can be defined by 3 points. Okay, the visual representation for the fact that the plane can be defined by 3 points. Let me see. I don't have paper here. I'll use this thing. Doesn't matter. See, your 3 points. A table doesn't need 4 legs. It can just have 3 legs. See, this thing. I'm holding this. Pretend this is a plane. I'm holding it up with just 3 fingers. No problem, right? See. Right here, and that's why 3 points define a plane, and that's a basic fact from Euclidean geometry. But as a result, however, 1 point and 1 line also define a plane, and then because the line contains 2 more points, and the entire line is contained in some plane, therefore a point in the line also defines a plane, and then similarly 2 intersecting lines define a plane. And so those are the 3 concepts we've learned so far that we already know from the past geometry or something, that those are things that you can use to define the plane. Here's a new one, okay? What we're going to do is that we are going to define the plane by 2 vectors. We'll have 2 vectors that is orthogonal, means perpendicular. So we have 2 vectors that's perpendicular, and we're going to grab one vector and then spin it. Your book says twist it. No, we're going to, well, whatever you call that. We're going to spin it, okay? And then so that the other vector will sweep out the plane because the angle is 90 degrees, like this. You just keep turning. See, the path of the bottom thing, imagine this thing is sweep out a whole circle, right? If my hand isn't moving, and if this thing really is perpendicular, then you'll sweep out, let's see, let me move over here, right? So you can see better. So you can sweep out a perfect plane if I'm doing it perfectly, which I'm not, but you get the idea. Okay, the path of the bottom part of the straw, see, is, imagine that's a plane. Sweep out the entire plane, because being that this is perpendicular, you can do that. So that is our definition of a plane. That is, our definition of a plane is 2 vectors who are orthogonal. What happens when they're orthogonal? The dot product is 0, okay? So the vector that's perpendicular to the plane, we'll call it the normal vector. Remember, normal means perpendicular. And then, and then we calculate the dot product is 0, and then we quickly come up with a bunch of equations for the plane, like this. So the equation of the plane is given by, first we have, which is n dot pq equal to 0. So what's n? N is just ABC, okay? And then p is x0, y0, z0. That's p. That's a fixed point. And because that's where n is perpendicular to the plane. And then q is any other point on the plane. Q is x, y, z. Therefore, when you do the dot product, then you come up with this equation that is the equation of the plane in space, okay, in all 3 dimensionals, x, y, and z, where a, b, c, and x0, y0, z0 are all constants. And that gives us the definition on the page of what this is. And then we have the dot product representation of the plane, which is the normal time dot, the normal dot pq, whereas q is any point, any and all points on the plane, whereas p is fixed. N dot pq equal to 0. From that we get this equation. There's a name for it, the scalar equation of a plane. Or this equation can also be represented like this, where d is all the numbers, and where ABC is multiplied by variables and d contains all the numbers. And that's the general form of the equation of a plane. So that is, and you notice the equation of a plane has no squares, okay? X, Y, and Z are only just the first degree. And any second degree planes is going to curve like the parabola and stuff like that. So, but the first degree, because the plane consists of all straight lines, right? So the plane has just first degree variables. Now, having said that, please do example 2.49 as part of your homework. Now, in example 2.49, you're giving 3 points, okay? And then to calculate the equation of the plane. Now, to do that, you have to first figure out what is the normal in order to fit that formula of ours. And in the definition, to figure out what the normal is, you pick the 3 points, right? You pick any 2 points which makes 2 vectors, and starting at the same point, and then do the cross product, which will give you the normal. It doesn't matter how long it is, just as long as it's exactly perpendicular. And with that, you will be able to write the equation of the plane. And similarly, the next example, 2.50, where you're given a point and a line. So from the line, you have to, again, figure out figure out the dot product, which is, well, figure out 2 vectors, okay, which are both in the plane, 2 different vectors, and that aren't parallel, of course. And then you do the dot product, sorry, what did I say dot? I mean cross product. Yeah, the other example too. I mean the cross product. And because the cross product applies, it will give you the answer to a cross product is perpendicular, right? You do the right-hand rule. You don't have to do the right-hand rule. This is just help you remember it. But you do the cross product, and then that will give you what a normal is, and with that you can write out the equation. So that's example 2.50. Please do that as part of your homework. So next, we are on page 197. Next page. Let's consider what is this again? This is, the distance from a point to a plane. How would you calculate the distance? Now let's say that you have a point, okay? And what you're gonna do is find some other point, any point on the plane. So your point, let's call it P, right? Here's your point. And then some other point on the plane, let's say is Q. And you need to find the distance from the point P to the plane, which is, it drops perpendicular down to the plane at R. But you don't know where R is. But we don't need to know that. See, that's the cute part of this trick. What you're going to do is you're going to calculate the normal of the plane, the n, by calculating two vectors and then do the cross product. Once you calculate the normal, you're going to do the projection of P onto n. That is, which is the height of this thing right here, this rectangle, okay? Which is the same as the distance from P to R. That is the height from, let me use this hand. The height from here to here, which is the projection of QP onto n. And that is the same as the distance. And that would be, and how would you do the projection? Well, there's a projection formula, which is on in your book page 156. And but you don't have to look it up because it's also on the next page. In case you try to remember what was the projection again? The projection of a vector onto another vector, in this case projection of QP onto n, is QP dot n. Projection is done by the dot product divided by the length of n. That is, if n isn't a unit vector. If it's a unit vector, of course, you don't have to do divide because the magnitude is just 1. So that is how you do the projection. A projection, basically, you can imagine, is at the shadow as the sun shines perpendicular to the line that you're projecting onto, and what is the shadow, and that is what you're calculating. The projection is also called comp, and the comp stands for component, okay? That is the component in that direction of the vector. Yeah, so that's how you calculate the distance between a plane and a point, and the perpendicular distance, which is also the shortest distance. And then with that, please do example 2.51 as part of your homework. Yeah, that's not as bad, okay? Next, let's look at page 199, parallel planes. Let's see. Two planes are parallel if their normals are parallel, okay? That is, imagine you have two planes and you have two vertical sort of like things sticking out, and the only way they can be parallel is if those two vertical things sticking out, like a needle or something, it sticks out, but those two things that's perpendicular are parallel to each other. Then if the two normal vectors are parallel, then the two planes are parallel themselves, otherwise they're not. So, and knowing that, then let's, to calculate the intersection of two planes, what you do is you have a simultaneous equation, two simultaneous equations, one for each plane, and then you just, solve for x. You solve x and, x and solve for y in terms of z. Because you have two planes, and then you let z be the parametric variable, the parameter t. Then everything comes out. You don't have to. You say, why does it have to be z? Z has to be t. It doesn't. It can be x, can be t, or y can be t. And your answer, if you do something differently, your answer might look slightly different. That's because the parametric equations are not unique, and as a result, the so-called the symmetric equations of the line are not unique either, because You can multiply them by numbers, for example, and the equation still holds. But in any case, that's how you would do example of 2.52. And so please do that as part of your homework. Next, let's look at page 201, where we're considering the angle between the two intersecting planes. What might the angle be? Now, the angle is related to the angle made by the two normals. In fact, the angle happens to be exactly the same. If you stare at it, then you realize that because of all the right angles, right? I mean, the normals are all at right angle to each other, which means theta here is the same as the, what is that, the complement or supplement or something, angle of this thing, which means theta is exactly that. Those two angles happen to be exactly the same. So the angle theta is the angle made between the two normals. And so with that, you can calculate, remember some formula from the previous section, where the angle between two vectors is the dot product divided by their normals, right? And in this case, we're just going to only accept the angle that's between 0 and 90 degrees. Because when two planes intersect, they have two angles, one's less than 90, one's bigger than 90, we don't really care. We just take the one that's less than 90, so we can use the absolute value, slap the absolute value on that formula, and that comes out with your equation. After of course, you have to work hard and figure out what the normals are. And the normals are figured out, well, either given to you. The normals for planes are actually quite direct. They just happens to be the coefficients of the variables. For example, that way, if you look at the definition, like for example, example A, part A, we have a bunch of x plus 2y minus z, right? The normal for A then for that plane is 1, 2, minus 1. See, just the coefficients. So they come up pretty quickly. And then so as a result, the answer for this example is quite convenient, which is nice. So please do example 2.53 as part of your homework. Next, let's look at page 202. We have previously talked about the distance between a point and a plane, and the distance we gave was this formula right here. And there's a way to shorten it slightly. That is, we put all those points into the formula, okay, where Q is ABC, and no, I said that wrong. I mean, Q is P is the point on the plane, etc., and then Q is the x1. So in any case, the point is we plug it into the formula to simplify a little and come up with a slightly shorter formula if the plane is given as ax plus by plus z plus k. Now, if that's the case, you plug it in and you quickly arrive at this slightly shorter formula. That is the distance from a point to a plane. Then you can plug in directly and not worry about the dot product or anything, because that's all included in the formula. So with that, please do example 2.54 as part of your homework. Now with that, we have come to the end of this section. For homework, please do the student project, well, after you finish the other stuff as the last homework. But please don't forget to do the student project, which shows you how to calculate the distance between two skew lines. And I will mention that after you finish the homework. I will talk about that. All right, so then for homework on the following page, we're going to do, please do page 207, problems 245, 49, 53, 57, 61, 69, 73, 75, 79, 83, 85, 89, 93, and 97. Now these problems are, again, vector problems in the beginning are fairly tedious, so please give yourself plenty of time and patience to grind through this stuff, because it's important to do them because you can get a feel of the 3 dimensions and maybe sometimes plot some of these graphs graphs of planes in space. A Desmos calculator allow you to do that, and you can Google how to do it. It's very simple. In the next section, I will go more into how to do it in the Desmos calculator. But for now, yeah, I have the link down here, how to graph on the 3D graph link for the Desmos calculator. So please go do your homework, and when you get back, I want to talk about the student project. Now that we are done with homework, let's talk about the student project on page 204. We're supposed to calculate the distance between two skew lines, which hasn't been covered in the book, but the book gives you a nice hint as to how to do it. You are given two skew lines, okay? Remember, skew lines they are in space. They are not parallel, but not intersect either. They don't do either one of those things. So knowing that, let's consider what happens. We have two skew lines, all right? And then the first thing you're going to do is you have two lines in space. You're going to find a line that's a vector on the first line. We'll call it V1. And then another vector on the second line. We'll call it V2. And well, you find some vector by finding a point on the line, subtracted by another point on the line, and that will be your vector, similar for the other vector. Once you have two vectors, you're going to do the cross product. That is, we'll have n equals to v1 cross v2. So you do the cross product, and sorry, there shouldn't be a bar there. You do the cross product, that gives you the normal vector. Okay, and then we'll make our normal vector to be 1 by dividing by the magnitude of whatever this cross product is, just for the convenience. So now our normal vector is unit 1. Now once you have the normal vector is perpendicular to both v1 and v2. Okay, so in other words, it is the normal vector is perpendicular to both lines. And it goes from one line to the other, but we don't know where. Where is it? And therefore so we still don't know how far the distance is, but we just know that there's a vector that connects the two, that goes from one to the other, that is perpendicular to both. Now to find out what that thing is, what we're gonna do is draw a box. Imagine a rectangular box. My marker is not so great. Here's my rectangular box, where in such a way that the first vector is on the top surface. Okay, v1 is somewhere here. Let's say v1 goes like this, and then this is v1, and then v2 is somewhere else. It goes like where v2 is on the bottom of the box, and it might be, I don't know, something like that. Doesn't matter how it goes. Okay, in such way, this is a rectangular box, and the top contains v1 and the bottom contains v2. And you think, how is that possible? I mean, what if the skew line is screwed up? But it doesn't matter how the skew line is skewed. You can always draw a box that's with top and bottom parallel sides that contains both lines. Just turn your box until it adjusts to both. It can be done. And how do I know it can be done? It just I guess that's one of those intuitive things, because there is a line perpendicular, and then and then we have some arrangement. Let me think. Actually, I just remembered something. Now, remember these two lines share the same normal. Okay, they have identical normals, which means they are contained in parallel planes, right? That is part of some parallel plane definition that we mentioned. As a result, you can find parallel planes such that this is everything is perpendicular. The plane is part of the box, top and bottom. All right, so let's say there's some normal line right here, whereas these angles are perpendicular. This is our n, okay? Except that our n is only size 1. So let's say the n goes, I don't know, it goes one way or the other. Let's say the n goes something like this. This is our n. And then what we're gonna do is find a point on V1, the line, doesn't matter where, and then find some other random point on V2, again, doesn't matter where, and then draw the box big enough so that it contains both points. And then we're going to connect these 2 points, and that is a vector, okay? We'll calculate this vector, and then we're going to project it onto n. If we project it onto n, that will give us the perpendicular distance. I'm not drawing it quite right, but the projection of this of this new thing, okay, let me stand over here. The projection of this thing onto n, which is my projection formula written right here, okay? In this case, which it means we need to calculate u dot v divided by the magnitude of u, that the length of this projection will be the distance between the two skew lines, and with that, you are done. And I'm not going to do that myself because that sounds like a lot of grunt work, but that's what's that. So you're supposed to do one example, which is on part 6. Okay, part 6, they give you 2 lines and ask you to do the calculations. So once you grind through it, and here's the answer should be 1.78. And if you get that, then your answer should be correct. And that is how you calculate the distance between skew lines. Now, the distance between skew lines, we could use differentiation maybe. You know, we can calculate the distance, any distance between them, and then take the derivative, find out when it's 0, and hope to find the minimum, that sort of thing. But that is, you know, in 3D is a complete pain. Let's not try that. Whereas this is much more straightforward, because, yeah, you just find the normal vector between the two of them. You do one cross product, and then you do the dot product, and you're done. So it's much better. Okay, so that's the end of this section.